I'd like to give the podium to Roger Dingledine. He's the project leader of the Tor project and will talk about security analysis of Tor.
Okay, hi everybody. I'm Roger Dingledine, the project leader for the Tor project, and I'm going to tell you a little bit more about ways that people can break Tor at this point, both practical and academic and theoretical. So there are a lot of things we could talk about today. I'm going to give you a crash course overview on Tor for people who don't have a good handle on how it works. And then I've actually skipped over all the stuff that we know how to do because that's not as interesting as the stuff that we don't know how to do. So we're going to spend most of our time on hard problems that are practical issues like application level vulnerabilities. And then we're going to focus on the research questions. There are a lot of people over the past year or two that have been coming up with really great academic research attacks that might be able to break Tor's anonymity. And then we can focus on what we're going to see over the next few years, and hopefully there will be time for some questions. So, big picture, Tor is an anonymity system. The idea is that there are a network of volunteers all around the internet, and they relay traffic for users. So users build a path through the network and connect to some website or IM server or something like that. And the goal is that somebody watching the local connection can't figure out what website you're going to, and somebody at the website side can't figure out where you're coming from. And ideally, no single place in the middle can learn both where you are and where you're going. So it's free software, open source. You can get it and use it and give it away. It comes with a specification and full documentation of this is exactly how you can build your own Tor. And several different groups in Germany and a fellow at Yale University built their own compatible Tor client. And it turns out that multiple implementations are a really good idea. It also means that a bunch of researchers used to look at the theoretic academic designs in anonymity and say, I bet this defense would work, I bet this attack would work, but then they never really had any way to test it. And now there's an actual Tor system out there, and we tell you exactly how it works, and you can analyze whether we got it right. And a lot of people are now actually trying out their defenses and trying out their attacks on the Tor network. And it turns out that most of the attacks work really well. So I don't know if that's a good result or a bad result, but at least now we can know it. There are about 1,500 relays all around the world relaying, I think it's something like 4 or 5 gigabits per second of traffic on average. So that's something up there with Hotmail and Wikipedia in terms of amount of traffic we push. There are some number of users. It's an anonymity system, so it's a little bit hard to count how many users we have. But I'm thinking a few 100,000, 200,000, 400,000, 100,000, something like that. The rest of you should learn your lesson about cell phones from this fine fellow in the front. So, as of the end of 2006, we're an official 501c3 nonprofit in the US, which means that people can give money to us and get tax deductibility for it. We also, as of next week, we're going to be hiring some more people, which will bring us up to 8 full-time developers, which is crazy talk, but I think we can make a lot of good use out of that. We've got a lot of different people funding us, different groups funding us. We were originally funded by the US Naval Research Lab, and then we were funded by the Electronic Frontier Foundation. So our claim to fame is that we're the only project to be funded both by the US DoD and the EFF for the same free software system. And since then, we've been funded by another US government group called the International Broadcasting Bureau. They're the folks who run Voice of America and Radio Free Cuba and things like that. They have some websites around the world that some people can't reach, and they'd like to fix that. And it turns out once you've built an anonymity system, a lot of people use it for circumvention or censorship resistance. They use it to be able to read BBC's website from places where otherwise it would be blocked. Okay, so Who cares about this stuff? When I'm talking to researchers and other academics, I tell them I work on an anonymity system. When I'm talking to my parents and my grandparents, I tell them I'm working on a privacy system. When I'm talking to corporations like eBay and Google and Walmart, I tell them I'm working on communication security or network security, because privacy is stupid, but good point, we do need communication security. And when I'm talking to governments and intelligence groups and law enforcement, I tell them I'm working on traffic analysis resistant communication networks. Because they already have security. They don't need this privacy stuff, and anonymity is scary, but good point, we do need to resist traffic analysis. So part of the challenge of this is figuring out how to talk to all of those different groups and bringing them into the same anonymity set so that they can blend together. Walmart cannot run its own anonymity system and just have Walmart people use it, because then everybody will know who's using the system. So you need all these different groups. And then there's the fourth category that we've been learning a lot more about in the past few years, of people who are behind restricted firewalls, either by governments or corporations or something like that. And now they use the same system for reachability. Now I can reach Voice of America's website, and before I couldn't. How do you build one of these? The easy answer is you put a computer out there somewhere, maybe in San Diego or something, and all the different Alices show up, and Alice 1 says, give me the front page of CNN, and Alice 2 says, give me the front page of Indie Media, and each user asks for something, and then the relay goes and fetches the answer and sends it back. And that works great, except if there's an attacker anywhere in the system. For example, if the relay in the middle is bad, then he gets to watch everything that everybody asks for. Or you can go bribe the janitor at the co-location building, or you can offer money to the CEO and he'll consider his business model. There are all sorts of different ways in which a central point of failure can fail. And you also don't have to actually attack the central point of failure to break in. You can also monitor the network going in and going out. For most of these single hop proxies, it's really just one cable the traffic goes in and out on. So if you can tap that, then you win for the entire network. So our goal is to distribute the trust. We want to have multiple different places that need to collaborate, that need to collude in order to figure out which Alice is talking to which Bob. So the idea is Alice is going to pick 3 hops and then connect to some Bob, and if the first guy is bad, if R1 is trying to figure out who's talking to who, he knows that Alice is using Tor, he just doesn't know where Alice is going, what Alice is doing. And if the last guy is bad, then he knows that somebody is talking to Bob, but he doesn't know who is talking to Bob. And if they're both bad, if R1 and R3 are colluding, then we give up, then we're screwed, because there are enough statistical attacks that you can look at the traffic pattern going into the network and watch the traffic pattern coming out of the network, and you can say, hey, wait, these line up. I'm pretty sure that this Alice is talking to this Bob. And then there's crypto, but I'm going to skip over that for the day. There are a couple of points to point out here. One of them is we use different layers of encryption at every step, which means that if you log the traffic between Alice and R1, and then you wait a few days, and then you try to break into one of them to force them to decrypt the traffic for you, it's too late. They've already thrown away the keys, and there's nothing on the relays. There's nothing on Alice, nothing on R1, nothing on R2 that can let you decrypt it. So you either have to break it right then, or you'll never be able to break the encryption. The other key point to notice on this slide is these white lines going from R3 to the various Bobs, those are not encrypted by Tor. Tor does not magically encrypt the internet. This is a little bit of a tricky thing for a lot of people because they say, well, I installed a security tool and now I'm secure. And turns out the internet's a little bit more complicated than that. So we'll talk about that a little bit more in a few slides. And there are directory servers. So one of the big questions when you're designing a system like this is, how does Alice learn the set of relays she can use? I mean, that's a great slide I've got right there, and we've got R1 and R2 and R3, but how does Alice learn that these are the relays she should use, and how does she learn their keys and their locations and things like that? So the idea is every server publishes a little summary of these are my keys and my address and which ports are open and my exit policy and so on. And it signs that with its identity key. And then it uploads that to the directory authorities. There are 6 of them right now. And then they talk amongst each other and produce a little summary network status consensus signed by as many of them as are willing to sign it. And then that gets cached on all the other relays, so Alice can go anywhere and she can get something, and if it has enough signatures on it, then she'll believe it. Okay, so that was the crash course on Tor. Hopefully everybody understands exactly how Tor works now, at least enough to make sense of the rest of the talk. So there are a bunch of different issues that we can talk about, and feel free to collect questions, and I'll be around all through the rest of the day to answer more questions. Okay, so last year there was this fellow in Sweden who was really good at manipulating the press. And he went to the press and said, I have an attack on the whole internet. It's great. I can watch everything, but I won't tell you what it is. And all of the press said, oh man, that brilliant Swedish hacker breaks internet. I must write the press article. So they all wrote the article about brilliant Swedish hacker breaks internet, won't say how. And then the next week, he went back to the press and said, I did it by running a Tor exit relay and I just watched all the traffic. Isn't that great? And then the press had already sort of gotten into the position where they had to publish because they'd already written the lead story before and now they had to write the follow-up. So he was pretty good at providing press. I haven't actually heard from him since the Swedish police raided him and took all his stuff and took him away. So I guess there are a couple of lessons here. One of them is generally wiretapping the internet without permission of the people you're wiretapping is against the law in most countries. So if you're planning to be a criminal, ask your lawyer first. I guess another lesson there is if you have an attack on Tor, you should come tell us about it first. I actually haven't heard from him before the Swedish police went and raided his system. I've never heard from him. I have no idea who this person is. So if you have an interesting attack on Tor, we'd love to hear from you. So another lesson is Tor hides your location, but it doesn't magically encrypt the whole internet. If you want SSL, if you want end-to-end encryption, then you should get it. You should use HTTPS, you should use POP-S, something like that. And it's a little bit trickier than that because Tor does protect against somebody watching your local network. If I'm on the DEF CON network or the CCC network, I'm going to use Tor when I'm using my unencrypted connections because, oh man, am I not going to use the network directly when I'm using my unencrypted connections. So it's a trade-off of where you want your attacker to be. And then it gets a little bit more complicated than that. A lot of websites use HTTPS as something that is a premium feature, that most people don't need that. Only the really special people are the ones who care a lot. So I was looking at the Wired article from last year about how all the Tor users are dumb because they don't use the encryption button. Shouldn't they just press the button and then they'll have their encryption? So I looked at Wired's website and they have a little login button at the top and they don't use SSL. They don't even support SSL. So it's a more fundamental issue than users on the internet are dumb and they should just click the button. A lot of places don't even let them do it. So we need to figure out some way to make end-to-end encryption and authentication more pervasive around the internet. What else can we do? We could configure the Tor client so that if you try to make a connection to port 23 or 110 or IMAP or something like that, then it pops up a little warning saying, hey, you just tried to make a connection to a port that is usually associated with an unencrypted or plain text connection. Let me teach you about encryption on the internet. That would work pretty well, I think. I mean, we'd have to figure out exactly how to phrase it because all the Windows users are trained just to click OK until things work. So do we make it actually fail by default, and then all the Windows users say, man, Tor sucks? I don't know the right balance of usability there. And even if we solve that one, what about port 80? Some stuff over port 80 is perfectly fine, but other stuff, I'm going to send my HT auth, I'm going to send various cookies. All of that stuff can be sensitive. Probably it's not encrypted, or at least not enough. So we can't solve this just by looking at ports and saying, I think you're being a bad person now, and I'm not sure if you're being a bad person then. And then there are some other options. Maybe we should educate users about how they need to use encryption on the internet. That trick never works. And there are some, I mean, it would be great to have some actual research on exit traffic properties. There was a group at Rice University and another group at Colorado University who actually ran an exit node, and they collected statistics about what came out of their exit node. And they have some interesting results. The majority of connections on the Tor network is web browsing. The majority of bytes on the Tor network is file sharing. So now we know that we need to do some sort of incentive system or balancing system or something so that the file sharers don't take over the whole network like they have taken over